Extreme Physics.
2012 APC Mechanics exam, question 3, which is a rolling problem. We got rolling, and we got sliding, and we got not sliding, and all right, these are always a good time. A ring of mass M and radius R is rolling. All right, so what do we got here? I did a similar problem like this before, and I think I had some billiard balls in there showing you what's going on. You can check that one out too. I should probably look it up. I don't remember. I'll flash it right here what year that was. I don't know offhand what it was. Very similar problem, really. All right, so we got this thing, and it's sliding only. It's on this frictionless surface, in this case, up to this point right here, in which case it's still sliding. So, but it's sliding and rotating. All right. Sliding and rotating. And then when it gets to L, this is a distance L, it's just rolling. It's no more slipping, right? No more slipping. And each case got a velocity this way. A ring of mass M and radius R of rotational inertia, mr squared, is initially sliding on a frictionless surface at a constant velocity v0 to the right as shown above. At time t equals 0, it encounters a surface with a coefficient of friction of mu and begins sliding and rotating. After traveling distance L, the ring begins rolling without sliding. Express all answers in terms of m, r, v0, mu, and fundamental constants as appropriate. Don't want to be inappropriate. Don't be inappropriate on the exam. They'll kick you out. Starting from Newton's second law in either translational or rotational form is appropriate. Again, be appropriate. Derive a differential equation that can be used to solve for the magnitude of the following as the ring is sliding and rotating. All right, so we're just going to derive the equation. We're not going to solve it yet. All right, this is A. All right, well, they told us what to do. Okay, so to find linear velocity, I guess we're working on I. Sum of the forces equal mass times acceleration. So we want a differential equation. That's an equation with a derivative in it. That could be used to solve for the magnitude of, in this case, the velocity. All right, well, let's draw a free body diagram. And this is during the sliding and rotating portion. So I probably should have that in contact there. So if I circle the object of interest, I'm going to draw myself a free body diagram. This is the y-axis. This is the x-axis. We have the normal force up, and we have the weight down. And we have friction, opposing motion. That's kinetic friction. That's kinetic friction. All right, so in the x direction, the acceleration's in the x direction. All right, it's accelerating that way. I'm going to say this is the general relationship, the vector relationship. Let's look at the components. Some of the forces in the x equal mass times the acceleration in the x. Well, we only have one force, so force of friction kinetic equals mass times, well, I want a differential equation that can be used to solve for v. So I just need to realize that the acceleration is dv dt. All right, I think I'm in pretty good shape, except I can't have that. Kinetic friction is coefficient of friction times the normal force, but the normal force in this case just equals the weight. And, oh, that should have been negative. That's a negative direction, and that's negative. All right, that's a negative direction. Make sure you have your directions in there. All right, so dv dt. All right, I think there's our differential equation. We got a derivative in it, and it's an equation, and it can be used to solve for v. All right, so I guess that would be I. Okay, the answer for I is minus mu g equals dv dt. All right, there's a differential equation. So let's take a look at question 2. The angular velocity. All right, so we're going to use Newton's second law in this one to sum of the torques equal moment of inertia times angular acceleration, like that. I need a torque diagram. Torque diagram. So I got my thing right here, and it's rolling, and it's sitting around the surface. And all right, so we have some forces here. We have friction this way, acting that way, and we have the normal force acting straight up, and the weight acting straight down. All right. So about the center, we're going to sum the torques about the center, and a moment of inertia about the center, because we know those things. All right. So about the center, here's the center right here. The weight can't provide a torque. It actually goes through the center, the weight vector, and so does the normal go like that. Actually, the weight vector actually originates at the center, and then the normal force also goes through the center. Neither of these can apply a torque, but a friction can, right? It has a right angle component. Our position vector is r right here, and then like that. So we have a torque, and that's kind of causing this. So that is a negative torque. So what do we have here? We have the torque is friction. It's negative friction times r. That's the torque due to friction. Equals the moment of inertia, and that's just a hoop. So it's mr squared. Alpha. Now, to make this a differential equation, I'm going to change alpha to d omega dt. Right? So alpha is d omega dt. Make sure you know your kinematics relationships. All right. Well, force of friction, this is kinetic, is going to be mu mg, coefficient of friction times the normal force, but the normal force equals the weight in this case. And r equals mr squared d omega dt. Let's just simplify this a little bit, and we end up with minus mu g. I'm going to bring r over. Mu g over r equals d omega dt. That's a differential equation, and that could be used to solve for omega, which is what we're looking for. All right, so I guess that is aye 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 aye. All right, let's erase. All right. Oh, these are all A. These are A. A I and A I I. Let's go look at B. I derive an expression for the magnitude of the velocity as the ring is sliding and rotating. All right. Well, since I have a differential equation, why don't I solve it? That's a good practice anyways. It's probably not necessary because it looks like we have a constant acceleration. And so we could actually use the kinematics equations, but let's actually solve this differential equation. Good practice. Good practice. All right. So what I would do is I would take that, and I'm going to solve that for v. And I'm going to say, all right, I'm going to separate the variables. Minus mu g, I'm going to bring the dt over to this side, equals dv. Like that. I just brought the t to the other side. I'm going to integrate both sides. This is a constant, so I'll keep that on the outside. T goes from 0 to t, and v goes from v0 to whatever velocity it is at time t. All right, so all right, this is minus mu gt, right? Because we would end up, well, I gotta go through the whole process, I guess. So if I integrate dt, I just get t, and t goes from t to 0 equals, and this is just v, v0 to v, and what do we got? Minus mu g t minus 0 equals v minus v0. All right, so let's just solve this for v. So we end up with v0 minus mu gt equals v. Right? What is that? B-I. B-I? B-I? Okay, and again, you could have used the kinematics equations there because the acceleration was constant. This is the acceleration. It was minus mu g. That was constant. Could have used kinematics equations. Always a good idea to practice your calculus. The angular velocity. We got to find that now. I think I'll solve that differential equation. Separate the variables. I started off with minus mu g over r equals d omega dt. Let's break up this fraction, bring dt over here. Minus mu g over r dt equals d omega. Like that. Run out of ink. I'm going to use a little circular motion to hopefully get some ink to the bottom. I'm going to integrate both sides. Like that. We'll go for t, we'll go from 0 to t. Oh, it worked. It's darker. And omega goes from omega initial to omega. Now that is 0 in that case. It's not rotating the beginning. So actually I could put 0 here. Well, I'll put omega 0. Its value is 0. All right, so we got minus mu g over r. That's just t. T0 equals omega. And I'll plug the value in. Omega 0 is 0. It's not rotating at first, right? It's just sliding at this point. So it's omega 0 is 0. Minus mu g over r t equals omega. All right, there we go. Let's see, does that make sense? Let's see. If time t equals 0, omega 0. Okay, good, and then it gets bigger with time, all right? Until we get to this point, in which case, once it gets here, this goes away. This doesn't count. This is rolling with slipping. And when this gets to L, this doesn't count either. Keep in mind there's a restriction on these, right? Let me just write this over here. That omega equals minus mu g over rt. Now both of these only for slide and rotate only, right? As soon as it gets here, these go away. They don't work anymore. They don't work here, and they don't work here. They only work in here, right? Because that was under the condition of sliding and rotating. That's an important idea right there. It's going to help us solve the later question. Derive an expression for the time it takes for the ring to travel distance L. All right. So how do we identify that point in time? How do we identify what happens when you get here? That's the key idea. What happens when you get there? Well, at this point, you're rolling while it's slipping. And under those conditions, now, right here, beginning here, we get V is that way. I'm going to say it's positive. Equals negative omega R, right? This thing's rolling like this. Is that the negative, right? V equals negative omega R right at that point. Well, what you need to realize is this is a transitional point. And this is a point where we had this equation, and this equation is true, and this equation is true, and this equation is true only at that point. After this point, these aren't true. Before this point, these are true, but that's not true. But right there, this is true, and these are true, right? So we're going to use that to solve our problem, right? That is what defines that position L. Or it's not really position L. He says that's a distance. Whatever that point is, whatever they call it. All right, we got to find the time. All right. Well, if we know V equals omega, all right, so we'll just do that. That's easy. V equals negative omega R. All right, so, well, that's V. So let's put that in there. V0 minus mu GT, right? That's V. It says right there. Must be true. It's written down. Negative times omega, which is minus mu G RT, times r. All right, so I just took omega, stuck it in there, replaced it there, and there we go. All right, so let's get rid of that. All right. What are we trying to find? We're trying to find time. Let's combine our times. V0 equals minus a minus is a positive, so we got mu gt plus mu gt. That looks like it's 2 mu gt. So V0 equals 2 mu gt. So T equals V0 over 2 mu g. I guess that's time. Next, what's the next question? Drive an expression for the magnitude. You know, really the difficult part was coming up with this idea. That's the one you have to understand. That's the conceptually tricky part. Because it's that threshold problem. You know, what's happening right at that transition. And, all right, so this is still true because we're still at that transition. They said, drive an expression for the magnitude of the velocity of the ring immediately after it's traveled L. All right, well, that doesn't seem like it's too hard. Velocity. You get the velocity. Velocity equals V0 minus mu gt. Let's plug T in. V equals V0 minus mu g times T, which is V0 over 2 mu g. Right? These go away. And we get V equals V0 minus V0 over 2, which is V0 over 2. Right? That is D. These have gotten significantly easier. Just kind of plugging in at this point. Drive an expression for the distance L. You know how this would have been a lot harder? It probably would have been a lot harder if they just gave you that initial information and then said, they asked you one question, they drive, how far is L? Right? That would have been harder. But anyways, they didn't. They kind of led us down the path. Drive an expression for the distance L. All right, well, how are we going to do that? Well, this is constant acceleration. Now, the first thing that came to mind was I would just use this. So I would just use that the distance something travels is just its average velocity times the time. We have the time, and we have the initial velocity and the final velocity, so we can get the average velocity. This would probably be the easiest way to do it. This is the way I'd probably do it. I would say, all right, so I know that average velocity is the initial velocity, since this is only true under constant acceleration, by the way, which this is constant acceleration. Average velocity is initial velocity plus the final velocity divided by 2. Right? So what do we get for average velocity? We got 3 halves v0. 3 halves v0 divided by 2, which is 3/4 v0. So that is our average velocity. So the distance traveled, which they're calling L, is 3 v0 over 4 times t, which is v0 over 2 mu g, which is 3 v0 squared over 8 mu g. Let's see, are my units working out here? What do we got? We got meters squared per second squared divided by meters per second squared. Yeah, we get meters. Maybe it's right. Might be right. This might be right. It might be. This very well could be right. You might want to check the key. Just think the units are right. Tell you that much. Units are right. So I can't say that it's definitely wrong, but it might be right. Hopefully that's the answer. I'll catch you a little later with more problems. See ya.
Extreme physics.